Picture this. Right now, as you listen to these words, billions of quantum events are unfolding in your brain. Electrons are tunneling through barriers that should be impossible to cross. Photons are dancing in superposition states. And according to some of the most brilliant minds in physics, these microscopic quantum phenomena might not just be background noise in your neurons, but, according to some interpretations, could play a role in awareness itself. This isn't science fiction. This is the radical theory that's dividing the physics community and challenging everything we thought we knew about the nature of mind and reality. Welcome back to another gentle exploration into the deepest mysteries of our universe. I'm here to guide you through one of the most controversial and fascinating frontiers in modern science, where quantum mechanics meets consciousness in ways that make even seasoned physicists uncomfortable. Tonight, we're diving into a theory so provocative that many researchers have spent decades trying to disprove it, while others have staked their entire careers on its revolutionary implications. As always, find a comfortable place to settle in. Let your breathing slow and your mind open to possibilities that stretch beyond our everyday understanding. This journey will take us from the smallest scales of reality to the vast questions of what it means to be conscious, aware, and alive in a quantum universe. Whether you're drifting off to sleep or staying alert for every detail, let these ideas wash over you like waves of possibility. Before we begin, I want to acknowledge something profound. The theory we're exploring tonight suggests that the very act of your consciousness engaging with these ideas could, in some speculative models, be linked to quantum processes. As speculative as that sounds, and as much as it remains unproven by current scientific standards, it's worth holding that thought gently as we proceed. Perhaps consciousness isn't just something that observes quantum mechanics. Perhaps consciousness has been proposed to involve quantum mechanisms. To understand why this theory has physicists so divided, we need to start with one of the most unsettling discoveries in the history of science. In the early 20th century, physicists began peering into the atomic realm and discovered something that defied all logic. Particles didn't seem to have definite properties until they were observed. They existed in what scientists call superposition, simultaneously occupying multiple states until the moment of measurement. This phenomenon, known as the observer effect, immediately raised uncomfortable questions. What exactly constitutes an observation? Does it require a conscious observer, or, as many interpretations hold, can interactions with the environment alone produce the same effect? These questions have haunted physics for over a century, and they've led some of the field's greatest minds to propose something radical: that consciousness itself might, in certain interpretations, play a role in understanding quantum mechanics. The story begins with Max Planck, the father of quantum theory, who believed that consciousness was more fundamental than matter itself. He once wrote that he regarded matter as derived from consciousness, not the other way around. This wasn't just philosophical speculation from a tired old scientist. Planck was making a profound claim about the nature of reality based on the strange behaviour he was observing in the quantum realm. Wolfgang Pauli, another quantum pioneer and Nobel laureate, went even further. He collaborated with the famous psychologist Carl Jung to study what they called synchronicity, partly because of the mysterious coincidences that seemed to surround his interactions with laboratory equipment. Pauli believed in psychokinesis, the idea that thought could influence matter, and he considered this worthy of serious scientific investigation. These were exploratory ideas rather than established scientific conclusions, but they show how deeply Pauli pondered the mind-matter relationship. These weren't fringe thinkers. These were the architects of quantum mechanics itself. Eugene Wigner, yet another Nobel laureate, developed what became known as the Wigner interpretation of quantum mechanics. He proposed that the wave function, the mathematical description of a quantum system's possible states, collapses specifically due to its interaction with consciousness. In his famous 1967 paper, Wigner wrote that the function of consciousness is to collapse the quantum mechanical state. This was presented as a hypothesis, not a proven mechanism, but it became one of the most famous attempts to connect consciousness with quantum behaviour. Take a moment here to consider what this means. If these physicists were correct, then consciousness isn't just an emergent property of complex brains. It's a fundamental feature of reality, as basic and essential as space, time, and energy. Your awareness, your subjective experience of being you could, in these speculative models, be woven into the fabric of the universe at the quantum level. The mainstream physics community largely sidestepped these uncomfortable implications by embracing what's called the Copenhagen interpretation, developed by Niels Bohr and his colleagues. This interpretation suggests that quantum particles don't exist in definite states until they're measured, but it carefully avoids specifying what constitutes a measurement or whether consciousness plays any special role. According to Copenhagen, when we're not looking, a quantum particle exists in a superposition of all possible states. It's simultaneously spinning up and down, here and there, existing and not existing. But the moment we observe it, this ghostly superposition collapses into a single, definite reality. The particle chooses a state, and that's what we see. This interpretation worked brilliantly for making predictions and building technologies. Quantum mechanics became the most successful theory in the history of science, enabling everything from lasers to computer chips to medical imaging. But it left a glaring philosophical hole. If observation causes collapse, what exactly counts as an observation? And why should the universe care whether anyone is looking? The Copenhagen interpretation essentially says, don't ask these questions, just shut up and calculate. And for decades, most physicists were happy to do exactly that. The math worked, the technology worked. Why worry about the deeper meaning? But some scientists couldn't let it go. They kept asking the uncomfortable questions, and in the 1990s, two researchers proposed an answer so radical that it sparked a scientific controversy that continues to this day. Roger Penrose, a mathematical physicist at Oxford University, and Stuart Hameroff, an anesthesiologist at the University of Arizona, looked at the mystery of consciousness and the mystery of quantum measurement and saw a connection. They proposed that these two puzzles might actually be the same puzzle. Their theory, called orchestrated objective reduction, or Orch OR, suggests that consciousness arises from quantum processes occurring within the microtubules of brain cells. Microtubules are tiny hollow structures that form the skeleton of neurons, and Penrose and Hameroff proposed that these structures might function as quantum computers, processing information through quantum superposition and entanglement. According to Orch OR, consciousness emerges when quantum superpositions in these microtubules reach a critical threshold and collapse into classical states. Each collapse represents a moment of conscious experience, a quantum tick of awareness. The theory suggests that our stream of consciousness is literally composed of these quantum collapse events, occurring roughly 40 times per second. This wasn't just speculation. Hameroff brought decades of experience studying anesthesia to the problem. He knew that consciousness could be turned on and off with remarkable precision using anesthetic gases, and he suspected that these drugs might work by disrupting quantum processes in microtubules. If consciousness were simply an emergent property of neural complexity, he reasoned, why would such small molecules have such profound effects on awareness? The theory faced immediate and harsh criticism. The brain, critics argued, is too warm, wet, and noisy for delicate quantum effects to survive. Quantum computers require temperatures near absolute zero to maintain coherence, isolated from any environmental interference. How could quantum processes possibly operate in the chaotic environment of a living brain? Physicist Max Tegmark calculated that quantum coherence in microtubules would last for less than a trillionth of a second in the brain's thermal environment. Compared to the millisecond timescales of neural processing, this seemed impossibly brief. The criticism was so withering that many dismissed Orch OR as pseudoscience. But then something unexpected happened. Scientists began discovering quantum effects in biological systems everywhere they looked. In photosynthesis, plants were found to use quantum coherence to transport energy with a remarkable efficiency. Birds appeared to navigate using quantum entanglement in specialized proteins in their eyes. Even our sense of smell has been proposed to involve quantum tunneling effects. As you absorb this information, notice how it challenges our assumptions about the separation between the quantum and classical worlds. The discovery that biological systems can maintain and exploit quantum effects at room temperature has forced scientists to reconsider what's possible in the warm, wet environment of the brain. In 2013, researchers discovered quantum vibrations in microtubules at room temperature, a finding some scientists interpreted as consistent with certain predictions of Orch OR. These weren't the fragile quantum states that critics had dismissed as impossible in biological systems. They were robust quantum effects that seemed to thrive in the cellular environment. More recently, in 2024, scientists discovered something even more remarkable: quantum superradiance in networks of tryptophan molecules within microtubules. Superradiance is a quantum phenomenon where molecules coordinate their energy emission in ways that should be impossible according to classical physics. The fact that this was occurring in the noisy environment of biological structures sent shockwaves through the scientific community. Dr. Anirban Bandyopadhyay, one of the researchers involved in this discovery, described it as potential evidence that microtubules may function as quantum orchestrators, coordinating the behavior of molecules across vast networks within the brain. This wasn't just a single quantum effect. It was interpreted as possible large-scale quantum organization in neural structures. Perhaps the most intriguing evidence for quantum consciousness comes from recent experiments with xenon gas. Xenon is a noble gas that's been used as an anesthetic for decades, but researchers noticed something puzzling. Different isotopes of xenon, which are chemically identical but have different quantum spin properties, produce different anesthetic effects. In 2018, Chinese researchers tested 4 different forms of xenon on mice and found that isotopes with larger quantum spin values were less effective at inducing anesthesia. This led some researchers to speculate that the quantum properties of the anesthetic molecules might influence how these drugs interact with neural systems involved in awareness. The implications are staggering. If consciousness depends on quantum effects, and if anesthetics work by disrupting these effects, then the very fact that we can be rendered unconscious by quantum spin differences has been interpreted by some as supportive of the idea that awareness itself could involve quantum phenomena. Neuroscientist Christoph Koch, who had been a vocal skeptic of quantum consciousness theories, admitted that if these results are confirmed, they might force him to reconsider his position. The experiments are now being replicated in multiple laboratories around the world, and the results could reshape our understanding of consciousness itself. Some researchers have proposed even more radical theories. Dr. Dirk Meyer at the University of Groningen suggests that consciousness might exist as a quantum field surrounding the brain, similar to the electromagnetic fields that surround magnets. In this view, the brain doesn't create consciousness, but rather has been proposed to tune into it, like a radio receiver, picking up signals from a broader field of awareness. This field theory of consciousness addresses one of the biggest puzzles in neuroscience, the binding problem. How do billions of separate neural processes combine to create a single, unified conscious experience? Classical theories struggle to explain this unity, but quantum field theories speculate that consciousness might be inherently unified at the quantum level, with individual brains serving as localized expressions of a more fundamental field. The mathematics behind these theories draws from quantum field theory, the same framework that describes fundamental particles and forces in physics. Just as the electromagnetic field can manifest as discrete photons when observed, the consciousness field has been proposed to manifest as discrete moments of awareness when it interacts with neural structures. This remains highly speculative, and no scientific consensus exists around these ideas. But the fact that serious researchers are proposing field theories of consciousness shows how far the discussion has evolved from the early days when quantum consciousness was dismissed as impossible pseudoscience. As we pause here, take a breath and consider the journey we've taken. We've moved from the historical foundations of quantum mechanics through the controversial proposals of Orch OR to the cutting-edge experiments that are reshaping our understanding of consciousness itself. The theory that once seemed impossible is gaining experimental support, while raising even deeper questions about the nature of mind and reality. What we're witnessing might mark the beginning of a revolution in our understanding of consciousness, one that could be as profound as the quantum revolution that transformed physics a century ago. The implications stretch far beyond academic debates. They touch on fundamental questions about what it means to be human, what it means to be aware, and what it means to exist in a quantum universe where consciousness and physics may, according to some models, be intimately connected. The story is far from over. In fact, we're just beginning to explore the deeper implications of quantum consciousness and the experimental evidence that's mounting in its favour. But first, we need to examine the resistance these theories have faced and why some of the most brilliant minds in physics remain deeply sceptical of the idea that consciousness could be a quantum phenomenon. But here's where the story takes a darker turn. Despite mounting evidence, the physics establishment has fought quantum consciousness theories with a ferocity that goes beyond normal scientific skepticism. This isn't just about experimental data or mathematical proofs. It's about something much deeper, the very soul of scientific materialism. Victor Stenger, a prominent physicist, characterized quantum consciousness as a myth with no scientific basis, placing it alongside gods, unicorns, and dragons. Stephen Hawking dismissed Roger Penrose's work as a kind of logical fallacy, arguing that just because consciousness is mysterious and quantum gravity is mysterious doesn't mean they're related. The language used by critics often carries an emotional charge that seems disproportionate to the scientific evidence. This resistance reveals something fascinating about the nature of scientific revolutions. Thomas Kuhn, in his groundbreaking work on the structure of scientific revolutions, observed that established paradigms don't simply yield to new evidence. They fight back, sometimes irrationally, because accepting new ideas means abandoning worldviews that have shaped entire careers and institutions. Consider what's at stake here. If consciousness were ever shown to be fundamental to quantum mechanics, it would challenge the assumption that science can study an objective reality independent of observers. It suggests that the universe might, in some interpretations, be viewed more like a participatory democracy than a deterministic machine. For scientists who've spent decades building careers on materialist assumptions, this represents more than just another theory to evaluate. It's an existential threat to their understanding of reality itself. The decoherence problem remains the strongest scientific objection to quantum consciousness. Critics like Max Tegmark have calculated that quantum states in warm biological systems should collapse within trillionths of a second, far too quickly to influence neural processing. This criticism seemed devastating when it was first proposed, and many researchers considered it the final word against quantum consciousness theories. But as you reflect on what we've already explored, notice how scientific certainties have a way of crumbling when new evidence emerges. The discovery of quantum effects in photosynthesis, bird navigation, and microtubule structures has shown that biological systems are far more quantum savvy than anyone imagined. The warm, wet, noisy environment that was supposed to destroy quantum coherence might actually protect and enhance it in some circumstances. Dr. Seth Lloyd at MIT has proposed that biological systems might use what he calls quantum Darwinism, where environmental interaction doesn't destroy quantum effects, but selects for the most stable ones. Instead of fighting decoherence, evolution may have learned to exploit it, creating quantum processes that can thrive in biological conditions rather than being destroyed by them. This represents a fundamental shift in how we think about the relationship between quantum and classical worlds. Rather than seeing them as separate realms with a sharp boundary, we're beginning to understand a more nuanced reality where quantum effects can persist and even flourish in classical environments under the right conditions. Some of the most intriguing research into quantum consciousness is happening in the most unlikely places. Deep beneath Gran Sasso Mountain in Italy, in laboratories shielded from cosmic radiation and electromagnetic interference, physicists have been conducting experiments that probe the fundamental nature of quantum collapse. These underground facilities were originally built to study exotic particles and dark matter, but they've become testing grounds for some of the most controversial theories in physics. In 2015, researchers used these pristine conditions to test aspects of the Diossi-Penrose model, a specific version of objective collapse theory related to Orch OR. The experiments involved measuring charged particles in ultra-pure germanium crystals, looking for traces of radiation that should be produced if gravity-related quantum collapse were occurring at the rates predicted by some theories. After 2 months of careful measurements, they found no evidence of such radiation, leading them to conclude that the simplest versions of gravity-based collapse models were highly implausible. But here's what's fascinating about negative results in science. They don't disprove entire theoretical frameworks, they refine them. The Gran Sasso experiments ruled out specific versions of objective collapse but left room for more sophisticated models. As the researchers themselves noted, more complex collapse theories could still be viable. This illustrates something beautiful about the scientific process. Even when experiments seem to challenge quantum consciousness theories, they actually help refine and improve them. Each test, whether positive or negative, adds another piece to an increasingly complex puzzle. Perhaps the most provocative research into quantum consciousness involves attempts to detect whether focused human attention can correlate with quantum systems directly. In recent years, several research groups have reported that when people focus their attention on photons passing through a double-slit apparatus, the interference pattern changes in ways that some analyses have interpreted as the wave function being influenced by consciousness. These experiments remain highly controversial and difficult to replicate consistently. The effects, when they occur, are subtle and require sophisticated statistical analysis to detect. Critics argue that any observed changes could be due to uncontrolled environmental factors or unconscious influences on the experimental apparatus. But proponents point out that the very difficulty of these experiments might tell us something important about consciousness itself. If consciousness were to influence quantum systems, we wouldn't expect the effects to be large or obvious. They might be precisely the kind of subtle statistical effects that require careful experimental design to detect. Dr. Dean Radin at the Institute of Noetic Sciences has conducted some of the most rigorous versions of these experiments, using automated systems and blind protocols to minimize human bias. His results, published in peer-reviewed journals, suggest small but statistically suggestive correlations between focused attention and quantum interference patterns. As you consider these experiments, notice how they push against the boundaries of what we consider scientifically acceptable. The possibility that consciousness could be correlated with quantum systems challenges fundamental assumptions about the separation between observer and observed that underlie the scientific method itself. This doesn't mean we should abandon scientific rigor or embrace unsubstantiated claims. It means we might need to develop new methodologies capable of studying phenomena that don't fit neatly into our current experimental frameworks. Science has always evolved by encountering mysteries that force it to expand its methods and concepts. Recent developments in quantum information theory have opened up entirely new ways of thinking about consciousness and reality. John Wheeler, the physicist who coined the term black hole, proposed that information might be more fundamental than matter or energy. He called this the it from bit principle, suggesting that physical reality may emerge from information processing at the most basic level. This information theoretic view of physics has profound implications for consciousness. If reality is fundamentally about information processing, then consciousness, which is arguably the most sophisticated information processing system we know, could play a much more central role in physics than we've traditionally assumed. Quantum information theory has also revealed deep connections between consciousness and fundamental physical principles like the holographic principle, which suggests that all the information contained in a volume of space can be represented on its boundary. Some researchers have proposed that consciousness might function similarly, with the rich inner experience of awareness emerging from information processing at the boundaries of neural networks. These ideas remain speculative, but they're grounded in solid mathematics and experimental physics. The holographic principle isn't just philosophy, it's been confirmed in string theory and black hole physics. If consciousness operates on similar principles, it would represent a profound connection between mind and the fundamental structure of reality. While microtubule-based theories like Orch OR have received the most attention, other researchers have proposed that consciousness might emerge from electromagnetic fields generated by neural activity. Dr. John Joe McFadden at the University of Surrey has developed what he calls the conscious electromagnetic information field theory. According to semi-theory, consciousness arises not from the firing of individual neurons, but from the synchronization of neural networks and the electromagnetic fields they generate. This field-based approach to consciousness might explain phenomena that are difficult for traditional neuroscience to address, such as the unity of conscious experience and the speed at which information is integrated across the brain. The electromagnetic approach has the advantage of being more experimentally tractable than quantum theories. Brain electromagnetic fields can be measured directly using techniques like EEG and MEG, and researchers have found correlations between field patterns and conscious states. During anesthesia, for example, the electromagnetic coherence of brain activity breaks down in ways that mirror the loss of consciousness. But electromagnetic theories also face challenges. Critics argue that electromagnetic fields in the brain are too weak and disorganized to support the kind of information processing that consciousness seems to require. The fields generated by neural activity appear to be more like noise than signal, lacking the structure necessary for coherent information processing. However, recent research has shown that even apparently random electromagnetic fields can exhibit hidden order when analysed with sophisticated mathematical techniques. What looks like noise at one level might reveal itself as structured information at another level, particularly when quantum effects are taken into account. The quantum consciousness debate has also revitalized interest in Pansychism, the ancient philosophical idea that consciousness is a fundamental property of all matter. Modern versions of Pansychism, influenced by quantum mechanics, suggest that consciousness might be an intrinsic feature of quantum fields, rather than something that emerges from complex arrangements of unconscious matter. This approach potentially solves what philosophers call the hard problem of consciousness, explaining how subjective experience arises from objective physical processes. If consciousness is fundamental rather than emergent, then the hard problem dissolves. We don't need to explain how consciousness arises from unconscious matter, because consciousness is already there at the most basic level. Physicist and philosopher David Chalmers has argued that panpsychist interpretations of quantum mechanics might provide the most elegant solution to the measurement problem in quantum physics, while simultaneously addressing the mystery of consciousness. If quantum events are associated with elementary forms of experience, then quantum measurement becomes a process of experiential selection rather than mysterious collapse. These ideas remain highly speculative and face significant objections from both physicists and philosophers. Critics argue that panpsychism leads to a combination problem. How do micro-experiences of individual particles combine to create the unified macro-experience of human consciousness? Quantum theories of consciousness attempt to address this by proposing that quantum entanglement and coherence might serve as the binding mechanisms that create unified conscious experience from distributed micro-experiences. If consciousness does involve quantum processes, then the human brain might be the most sophisticated quantum computer in the known universe. This isn't just metaphor, it's a serious hypothesis with testable implications. Quantum computers can solve certain problems exponentially faster than classical computers by exploiting superposition and entanglement. If the brain operates as a quantum computer, it could help explain some of the remarkable capabilities of human cognition that seem difficult for classical neural networks alone to account for. Consider pattern recognition, creativity, and intuition. These cognitive abilities often involve making connections across vast amounts of information in ways that seem to defy classical computation. A classical computer must search through possibilities sequentially, but a quantum computer can explore multiple possibilities simultaneously through superposition. Dr. Henry Stapp, a quantum physicist at UC Berkeley, has proposed that quantum mechanics provides the theoretical framework for understanding how consciousness can exercise what we experience as free will. In his model, conscious observation selects specific outcomes from the quantum superposition of brain states, providing a mechanism for top-down causation that doesn't violate physical laws. This quantum approach to free will remains controversial, but it addresses a genuine puzzle in neuroscience. If the brain is purely classical, then all our decisions should be determined by prior physical states. But quantum mechanics introduces genuine randomness, an observer effect that some researchers believe could provide space for genuine choice and agency. As you contemplate these ideas, take a moment to notice your own experience of consciousness right now. The seamless flow of thoughts and perceptions, the way attention moves effortlessly from one idea to another, the unified sense of being a conscious observer. These features of experience have been interpreted by some as potentially consistent with quantum processes operating in your brain at this very moment. This remains unproven by current scientific standards, but the possibility adds a layer of mystery to the simple act of being aware. Recent research has revealed that brain structures exhibit fractal properties at multiple scales, from the branching patterns of neurons to the folding of the cortex itself. Fractals are mathematical objects that display similar patterns at every level of magnification, creating infinite complexity from simple rules. If consciousness involves fractal quantum processes, it might offer one explanation for how the finite neural networks of the brain can generate the seemingly infinite richness of conscious experience. Dr. Paola Zizzi at the University of Padova has proposed that consciousness emerges from fractal quantum processes that operate across multiple scales simultaneously. In this model, quantum effects at the molecular level organize into larger scale patterns that eventually manifest as conscious experience. The fractal structure provides a natural bridge between the microscopic quantum realm and the macroscopic world of neural networks and behavior. These fractal approaches to consciousness suggest that awareness might have a kind of scale-invariant structure, with similar patterns appearing at the level of molecules, cells, neural networks, and whole brains. This could explain why consciousness seems to be both localized in specific brain regions and distributed across the entire nervous system simultaneously. The resistance to quantum consciousness theories has been significantly weakened by the broader revolution in quantum biology. What was once considered impossible, quantum effects operating in warm, wet biological systems, is now recognized as commonplace. Photosynthesis, the process that powers most life on Earth, relies on quantum coherence to achieve near-perfect energy transfer efficiency. Bird navigation uses quantum entanglement in cryptochrome proteins to sense magnetic fields. Even our sense of smell has been proposed to depend on quantum tunneling effects that allow us to distinguish between molecules with identical shapes but different vibrational frequencies. This quantum biology revolution has forced scientists to reconsider their assumptions about the relationship between quantum and classical physics. Rather than existing in separate realms, quantum and classical effects appear to be intimately connected in biological systems. Evolution has been hypothesized by some researchers to have learned to exploit quantum mechanics, not despite the warm, noisy environment of living systems, but because of it. The implications for consciousness research are profound. If biological systems routinely use quantum effects for information processing, energy transfer, and sensing, then the brain, the most complex biological information processing system known, could, in some interpretations, also rely on quantum mechanisms. The question isn't whether quantum effects can survive in the brain, but how evolution might have learned to exploit them for the sophisticated information processing that underlies consciousness. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. In a development that would have seemed like science fiction just a few years ago, Google's Quantum Artificial Intelligence Lab is now conducting research into quantum theories of consciousness. Dr. Hartmut Neven, who leads the lab, has proposed experiments that aim to explore whether human brains can interact with quantum computers in ways that suggest conscious quantum effects. These experiments involve creating attempted quantum entanglement between human brain activity and qubits in quantum processors. The idea is that if consciousness involves quantum processes, there might be subtle, measurable correlations between brain states and quantum systems that couldn't be explained by classical physics alone. The fact that one of the world's leading quantum computing labs is taking these ideas seriously represents a significant shift in the scientific landscape. Google's quantum computers are among the most sophisticated ever built, and their willingness to explore consciousness applications suggests that quantum theories of mind are moving from fringe speculation into areas of cautious scientific interest. These experiments remain in early stages and the results are far from conclusive. But the very fact that they're being conducted with state-of-the-art quantum technology marks a new phase in consciousness research. We're moving from philosophical speculation to direct experimental investigation of the possible quantum nature of mind. Perhaps the most promising approach to quantum consciousness comes from information integration theory, developed by neuroscientist Giulio Tononi. This theory proposes that consciousness corresponds to integrated information, the amount of information generated by a system that's more than the sum of its parts. Quantum versions of information integration theory suggest that consciousness might emerge from quantum information processing that creates integrated wholes from separate parts. Quantum entanglement provides a natural mechanism for this integration, allowing separate brain regions to share information in ways that classical physics cannot fully explain. This approach has the advantage of being mathematically precise and potentially measurable. Researchers can calculate the integrated information of different brain states and correlate these measurements with levels of consciousness. Early results suggest strong correlations between integrated information and conscious awareness, providing empirical support for information-theoretic approaches to consciousness. The quantum version of this theory goes further, proposing that the integration occurs through quantum coherence and entanglement rather than classical neural connections alone. This would explain why consciousness seems to have a unified, holistic quality that's difficult to reduce to separate neural processes. As we near the end of this exploration, take a breath and consider how far we've travelled together through these ideas. We've moved from the historical foundations of quantum mechanics through cutting-edge experiments and theories that challenge our most basic assumptions about consciousness and reality. The landscape of consciousness research is shifting beneath our feet, with quantum theories moving from the margins to the mainstream of scientific investigation. What emerges from this journey is not a definitive answer about whether consciousness is quantum mechanical, but rather a deeper appreciation for the complexity and mystery of awareness itself. Whether consciousness turns out to be classical, quantum, or something else entirely, the questions we've explored tonight touch on the deepest puzzles of existence. What does it mean to be conscious? How does subjective experience arise from objective reality? And what is the relationship between mind and the fundamental structure of the universe? These questions don't have easy answers, but they invite us into a sense of wonder about our place in the cosmic story. Every moment of consciousness, every thought and sensation could be viewed as potentially connected to the quantum foundations of reality in ways we're only beginning to understand. That possibility alone is enough to transform how we think about ourselves and our relationship to the universe we inhabit. In our next exploration, we'll dive even deeper into these quantum mysteries by examining whether the wave function, that mathematical description of quantum possibilities, might actually exist as a physical reality rather than just a calculational tool. The question of quantum consciousness explained and whether the wave function actually exists will take us to the very heart of what reality means in a quantum universe. Until then, rest well, and remember that every dream, every moment of awareness might be a whisper from the quantum realm, where consciousness and cosmos meet in the endless dance of possibility and actuality. But sometimes the most profound discoveries happen in the most unexpected places. Deep beneath the Italian Alps, in laboratories carved from solid rock and shielded from cosmic radiation, physicists have been conducting experiments that probe the very boundary between quantum and classical reality. These underground facilities, originally designed to hunt for dark matter and exotic particles, have become testing grounds for some of the most fundamental questions about consciousness and quantum mechanics. In these pristine conditions, researchers can create environments cleaner and quieter than outer space itself. Here, they've been testing whether the collapse of quantum wave functions might leave detectable traces, signatures that could reveal the mechanism by which quantum possibilities become classical realities. The experiments involve monitoring ultra-pure crystals for months at a time, searching for the faintest whispers of radiation that might accompany quantum collapse events. The results have been both illuminating and puzzling. While some predicted signatures of collapse haven't been found, the experiments have revealed new subtleties in how quantum systems behave when truly isolated from environmental interference. Rather than simply confirming or denying quantum consciousness theories, these underground explorations have opened up new questions about the nature of quantum measurement itself. As you contemplate these subterranean searches for quantum truth, consider how our understanding of consciousness might be like these deep excavations. We're digging beneath the surface of ordinary experience, looking for the fundamental processes that might underlie awareness itself. The answers we find might not be what we expected, but they're reshaping our understanding of what it means to be conscious in a quantum universe. Perhaps nowhere is the connection between quantum physics and consciousness more tangible than in the operating room. For over a century, doctors have been able to reversibly eliminate consciousness using anesthetic gases. Yet the mechanism by which these molecules erase awareness has remained largely mysterious. Classical neuroscience suggests that anesthetics work by disrupting neural communication, but recent discoveries have revealed something far stranger. In 2018, researchers in China made a discovery that sent ripples through both the anesthesia and consciousness research communities. They were studying xenon, a noble gas that's been used as an anesthetic since the 1950s. But they noticed something peculiar about different isotopes of the same element. Xenon-129 and Xenon-131, while chemically identical, have different nuclear spins, a purely quantum property related to the intrinsic angular momentum of atomic nuclei. When these researchers tested different xenon isotopes on laboratory mice, they found something unprecedented. The isotopes with different quantum spins produced measurably different anesthetic effects. Xenon-129, with its larger nuclear spin, was less effective at inducing unconsciousness than Xenon-131. This was interpreted by some as the first clear evidence that quantum properties of molecules could influence consciousness. The implications are staggering. If anesthetics work by disrupting quantum processes in the brain, and if different quantum spins produce different effects on consciousness, then awareness itself may be sensitive to quantum mechanical properties. This isn't theoretical speculation. This is experimental evidence that consciousness appears to respond to quantum variables in ways that classical neuroscience cannot yet fully explain. Dr. Christoph Koch, one of the world's leading consciousness researchers and a long-time skeptic of quantum theories of mind, has admitted that these results forced him to reconsider his position. The xenon experiments suggest that consciousness might indeed be sensitive to quantum properties in ways that challenge our fundamental assumptions about the nature of awareness. These findings are now being replicated in laboratories around the world using increasingly sophisticated experimental designs. Researchers are testing other anesthetic gases with different quantum properties, looking for patterns that might reveal the quantum basis of consciousness. If confirmed, these experiments could revolutionize both anesthesiology and our understanding of consciousness itself. While experimental evidence accumulates, theoretical physics has undergone its own revolution that's transforming how we think about consciousness and reality. This revolution centers around information theory and the radical idea that information, not matter or energy, might be the most fundamental aspect of the universe. John Wheeler, the physicist who coined the term black hole and mentored many of the giants of modern physics, proposed a principle he called it from bit. Wheeler's insight was that physical reality might emerge from information processing rather than the other way around. In this view, matter and energy are manifestations of underlying information structures, patterns of data that organize themselves into the phenomena we experience as physical reality. This information theoretic approach to physics has profound implications for consciousness. If reality is fundamentally about information processing, then consciousness, which is arguably the most sophisticated information processing system we know of, could play a central role in the structure of reality itself. This perspective suggests that the hard problem of consciousness, explaining how subjective experience arises from objective processes, might be based on a false premise. Perhaps consciousness isn't something that emerges from unconscious matter, but rather something that information processing systems naturally possess at various levels of complexity. Quantum mechanics fits naturally into this information theoretic framework. Quantum systems can be understood as information processing devices that manipulate quantum bits, or qubits, rather than classical bits. A qubit can exist in superposition, simultaneously representing multiple information states until a measurement forces it to choose a definite value. If consciousness involves quantum information processing, then awareness itself might operate through the manipulation of quantum information states. This quantum information approach to consciousness addresses several puzzles that have long plagued consciousness research. The binding problem, for example, asks how separate neural processes combine to create unified conscious experience. Quantum entanglement provides a natural mechanism for binding, allowing separate information processing events to become correlated in ways that classical physics cannot explain. As you reflect on these ideas, notice how they invite us to think differently about the relationship between mind and reality. Rather than consciousness being something that observes an independent physical world, consciousness might be an intrinsic aspect of the information processing that constitutes reality itself. This remains speculative, but it represents a profound shift from the materialist assumptions that have dominated neuroscience and physics for centuries. Not all quantum theories of consciousness focus on microtubules and molecular processes. Some researchers have proposed that consciousness might emerge from the electromagnetic fields generated by neural activity, fields that might even exhibit quantum properties under certain conditions. This electromagnetic approach, developed by scientists like Dr. John Joe McFadden at the University of Surrey, suggests that awareness arises from the coherent electromagnetic field patterns that emerge when neurons fire in synchrony. The human brain generates electromagnetic fields through the collective activity of billions of neurons. These fields can be measured using techniques like electroencephalography and magnetoencephalography, which detect the electrical and magnetic signatures of neural activity. McFadden's conscious electromagnetic information field theory, or CEMI theory, proposes that consciousness corresponds to specific patterns of electromagnetic coherence across neural networks. What makes this theory particularly intriguing is its potential connection to quantum mechanics. Electromagnetic fields, even in biological systems, can exhibit quantum properties under certain conditions. Quantum coherence in electromagnetic fields has been proposed as one possible way to provide the unity and integration that characterizes conscious experience, binding separate neural processes into coherent patterns of awareness. During anesthesia, researchers have observed that the electromagnetic coherence of brain activity breaks down in specific ways. The normal patterns of field synchronization that characterize waking consciousness dissolve, replaced by fragmentary, incoherent field activity. This correlation between electromagnetic coherence and conscious states provides support for field theories of consciousness, though the quantum aspects remain speculative. The electromagnetic approach has several advantages over purely molecular theories of quantum consciousness. Electromagnetic fields in the brain are robust and can maintain coherence over relatively long timescales compared to molecular quantum states. They also provide a natural mechanism for the rapid integration of information across different brain regions, something that's essential for unified conscious experience. However, electromagnetic theories also face challenges. Critics argue that the brain's electromagnetic fields are too weak and noisy to support the kind of complex information processing that consciousness seems to require. The fields generated by neural activity appear more like background noise than organized signals, lacking the structure necessary for coherent information processing. But recent advances in understanding complex systems have shown that apparent noise can hide sophisticated organization. What looks random at one level of analysis might reveal deep structure when examined with the right mathematical tools. If consciousness involves electromagnetic field patterns with quantum properties, we might need new analytical techniques to detect and understand their organization. One of the most beautiful discoveries in neuroscience has been the fractal structure of brain organization. From the branching patterns of individual neurons to the folding of the cerebral cortex, the brain exhibits similar patterns at multiple scales of organization. This fractal architecture might provide a clue to understanding how quantum effects could scale up from molecular processes to create macroscopic consciousness. Fractals are mathematical objects that display self-similar patterns at every level of magnification. They create infinite complexity from relatively simple rules, generating structures that are simultaneously finite in overall size but infinite in detail. If consciousness involves fractal quantum processes, it has been proposed by some theorists that this might help explain how the finite neural networks of the brain can generate the seemingly boundless richness of conscious experience. Dr. Stuart Kauffman, a theoretical biologist and complexity theorist, has proposed that consciousness might emerge from fractal quantum processes that operate across multiple scales simultaneously. In this model, quantum effects at the molecular level organize into larger scale patterns through fractal scaling relationships. These patterns eventually manifest as the unified field of conscious awareness, but they maintain connections to quantum processes at smaller scales. This fractal approach addresses one of the key challenges facing quantum theories of consciousness: the scale problem. How do molecular quantum effects influence the large-scale neural processes that seem to correlate with conscious states? Fractal scaling provides a hypothetical bridge, showing how patterns can propagate across scales while maintaining their essential structure. Experimental evidence for fractal organization in consciousness comes from studies of brain activity during different states of awareness. Researchers have found that conscious states are characterized by fractal patterns in neural oscillations, with similar rhythmic structures appearing at multiple temporal scales. During unconscious states, these fractal patterns break down, replaced by more random or periodic activity. The mathematical tools needed to study fractal quantum processes are still being developed, but early work suggests that such systems might have remarkable information processing capabilities. They could potentially integrate information across multiple scales simultaneously, while possibly maintaining quantum coherence through fractal self-organization. As you consider these fractal dimensions of consciousness, imagine the possibility that your awareness right now might be manifesting similar patterns at multiple scales. From quantum processes in individual neurons to the large-scale rhythms of neural networks, consciousness might be a fractal phenomenon that some researchers believe could bridge the quantum and classical worlds through mathematical beauty and complexity. One of the most profound developments in modern physics has been the discovery of the holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary. This principle, which emerged from studies of black hole physics and string theory, has revolutionized our understanding of space, time, and information. Some researchers now propose that consciousness might operate according to similar holographic principles. The holographic principle emerged from attempts to understand what happens to information when it falls into a black hole. Stephen Hawking's work showed that black holes emit radiation and eventually evaporate, but this led to a paradox. If information cannot be destroyed, as quantum mechanics requires, what happens to the information that falls into the black hole? The resolution came from the realization that the information is encoded on the black hole's event horizon its two-dimensional boundary rather than in its three-dimensional interior. This discovery suggested that three-dimensional reality might emerge from information processing on two-dimensional boundaries, a principle that's been confirmed in various theoretical contexts. If consciousness operates holographically, then the rich three-dimensional experience of awareness might emerge from information processing on lower-dimensional neural boundaries or surfaces. Dr. Stuart Hameroff and others have proposed that microtubules might function as holographic information processing systems, encoding conscious experience in their cylindrical boundary surfaces while maintaining quantum coherence throughout their structure. This holographic approach could potentially explain how consciousness maintains both local specificity and global integration, characteristics that are difficult to understand in purely classical neural network models. The holographic principle also provides a new perspective on the relationship between subjective experience and objective neural processes. Rather than consciousness being an emergent property of complex neural activity, it might be a fundamental aspect of how information is organized and processed in biological systems. The subjective richness of conscious experience might reflect the holographic encoding of information across neural boundaries. This holographic view of consciousness remains highly speculative, but it's grounded in established mathematical frameworks within theoretical physics. The mathematical frameworks that describe holographic information processing in black holes and string theory are being adapted to model biological information processing systems. While we're still far from a complete holographic theory of consciousness, the conceptual framework provides new tools for thinking about the relationship between mind and brain. If consciousness does operate holographically, it would represent a profound connection between subjective experience and fundamental physics. The same principles that govern the behavior of black holes and the structure of space-time might also underlie the organization of awareness and the nature of subjective experience. Evolution has been shaping biological information processing for billions of years, and recent work in quantum biology suggests that natural selection has learned to exploit quantum mechanics in sophisticated ways. This raises a fascinating question. Might evolution have discovered quantum consciousness as a solution to the information processing challenges faced by complex organisms? Dr. Seth Lloyd at MIT has developed a theoretical framework called quantum Darwinism, which describes how classical reality emerges from quantum processes through environmental selection. In this model, the environment doesn't simply destroy quantum coherence through decoherence, but rather selects for the most stable and useful quantum states while eliminating others. Applied to consciousness, quantum Darwinian selection has been suggested as one possibility to explain how evolution discovered quantum information processing strategies that are robust in biological environments. Rather than fighting against decoherence, evolution might have learned to harness it, creating quantum processes that thrive in the warm, wet conditions of living systems. This evolutionary perspective on quantum consciousness provides a potential answer to critics who argue that quantum effects are too fragile to influence biological processes. If quantum consciousness provides adaptive advantages, natural selection would favour organisms that can maintain and exploit quantum coherence in biological conditions. Over billions of years of evolution, this could lead to sophisticated quantum information processing systems that are perfectly adapted to biological environments. The adaptive advantages of quantum consciousness might include enhanced pattern recognition, improved decision-making under uncertainty, and more efficient information integration across neural networks. These capabilities could provide significant survival advantages, particularly for organisms facing complex environmental challenges that require rapid information processing and flexible behavioral responses. Recent research in quantum biology has shown that evolution has indeed discovered quantum solutions to biological information processing problems. Photosynthesis uses quantum coherence to achieve near-perfect energy transfer efficiency, while bird navigation relies on quantum entanglement to sense magnetic fields. If evolution can discover quantum solutions to these problems, it has led some researchers to ask whether it might also have discovered quantum approaches to consciousness. This evolutionary framework also suggests testable predictions. If consciousness involves quantum processes that have been shaped by natural selection, we might expect to find evidence of optimization and efficiency in these systems. Quantum processes in the brain should show signs of evolutionary fine-tuning, with parameters and structures that maximize information processing capabilities while maintaining stability in biological environments. Take a moment here to consider the deep timescales involved in these evolutionary processes. The quantum consciousness you might be experiencing right now could be the product of billions of years of evolutionary experimentation with quantum information processing. Every thought, every moment of awareness might represent the culmination of an ancient dialogue between quantum mechanics and natural selection. In what represents perhaps the most significant development in quantum consciousness research, Google's Quantum Artificial Intelligence Lab has begun conducting experiments that aim to probe the relationship between human consciousness and quantum systems. Dr. Hartmut Neven, who leads Google's quantum computing efforts, has proposed experiments that could explore whether quantum effects appear in aspects of conscious experience. These experiments involve creating controlled interactions between human brain activity and state-of-the-art quantum computers. The basic idea is to test whether conscious attention or intention can influence quantum systems in ways that would be impossible according to classical physics. If consciousness involves quantum processes, there might be subtle, statistically detectable correlations between brain states and quantum system behavior that couldn't easily be explained by chance or classical interactions. The experimental protocols are remarkably sophisticated, using quantum entanglement, superposition, and measurement to create controlled tests of quantum consciousness hypotheses. Participants are connected to EEG systems that monitor their brain activity while they attempt to influence quantum systems through focused attention or intention. The quantum systems themselves are isolated in controlled environments to eliminate classical interference. Early results from these experiments remain preliminary and controversial, but they represent an unprecedented application of cutting-edge quantum technology to consciousness research. The fact that one of the world's leading quantum computing labs is taking these ideas seriously represents a significant shift in the scientific landscape. Google's quantum computers are among the most sophisticated ever built, capable of maintaining quantum coherence for increasingly long periods and performing calculations that would be impossible for classical computers. If these systems can detect quantum signatures associated with human conscious activity, it would provide a potentially meaningful line of evidence for quantum theories of mind. The experiments also explore whether quantum computers might enhance human cognitive abilities through quantum classical interfaces. If consciousness involves quantum information processing, then hybrid systems that combine human brains with quantum computers might achieve information processing capabilities beyond what either system could accomplish alone. These possibilities remain highly speculative, but the research represents a new frontier in both consciousness studies and quantum technology. We might be witnessing the first steps toward a hypothetical technological interface between quantum mechanics and human awareness, with implications that extend far beyond current scientific understanding. At the heart of quantum mechanics lies a profound mystery known as the measurement problem. Quantum systems exist in superposition, simultaneously occupying multiple states until they're measured. But what exactly constitutes a measurement? And why should the universe care whether anyone is looking? These questions have puzzled physicists for nearly a century, and they're intimately connected to questions about consciousness and observation. In the standard interpretation of quantum mechanics, measurement causes the wave function to collapse from a superposition of possibilities into a single, definite state. But the theory provides no clear definition of what constitutes a measurement or why collapse occurs. This ambiguity has led to numerous interpretations, from the many worlds theory, where all possibilities occur in parallel universes, to objective collapse theories, where the wave function is physically real and undergoes spontaneous collapse. Some interpretations propose that consciousness plays a special role in quantum measurement. In these consciousness-based interpretations, the observer's awareness is what triggers wave function collapse, transforming quantum possibilities into classical realities. This would make consciousness in these models not just an emergent property of physical processes, but a hypothetically fundamental aspect of how reality itself is constructed. The consciousness interpretation faces significant challenges. If consciousness causes wave function collapse, then what about unconscious measurements performed by detectors and instruments? Do these systems also collapse wave functions, or do they remain in superposition until observed by a conscious being? These questions push the interpretation to its limits and force us to consider what consciousness actually means in quantum mechanical terms. Recent experiments have attempted to test consciousness-based interpretations by examining whether focused human attention can influence quantum systems in detectable ways. While results remain controversial and difficult to replicate consistently, some studies have reported small but statistically significant correlations between conscious intention and quantum system behavior. Dr. Dean Radin at the Institute of Noetic Sciences has conducted some of the most rigorous versions of these experiments, using double-slit interference patterns as test systems. Participants attempt to influence the interference pattern of photons passing through a double-slit apparatus through focused attention, while sophisticated monitoring systems record both the quantum behavior and the participants' neural activity. The reported effects are subtle and require careful statistical analysis to detect, but they have been interpreted by some researchers as potentially suggesting that consciousness might indeed play a role in quantum measurement under certain conditions. These experiments remain at the margins of mainstream science, but they represent serious attempts to test fundamental questions about the relationship between mind and quantum reality. As you consider these measurement mysteries, notice how they challenge our basic assumptions about the relationship between observers and observed. If consciousness does play a role in quantum measurement, then the boundary between subjective experience and objective reality becomes blurred in profound ways. The very act of awareness might be metaphorically viewed as a creative force in the universe, participating in the ongoing construction of reality from quantum possibilities. Moving beyond microtubuli and electromagnetic theories, some researchers have proposed that consciousness might exist as a fundamental field, similar to the electromagnetic field or the Higgs field that gives particles their mass. In these field theories, consciousness isn't produced by neural activity, but rather is conceptualized as being accessed or tuned into by appropriately organized brain structures. Dr. Dirk Meyer at the University of Groningen has developed one of the most sophisticated versions of field theory consciousness. His model proposes that consciousness exists as a quantum information field that hypothetically extends throughout space, with individual brains serving as localized receivers or antennae that tune into specific frequencies or patterns within this field. This field approach addresses several puzzles in consciousness research. It explains why consciousness seems to have a unified, field-like quality that can't be reduced to separate neural processes. It also provides a mechanism for phenomena like intuition, creativity, and sudden insights that seem to emerge from beyond ordinary thought processes. If consciousness exists as a field, then the brain's role would be more like that of a radio receiver than a generator. Different brain states would correspond to tuning into different aspects or frequencies of the consciousness field. Damage to the brain wouldn't destroy consciousness, but would impair the brain's ability to access and express it. This perspective has parallels with ancient philosophical traditions that view consciousness as fundamental to reality rather than emergent from matter. But field theories of consciousness attempt to ground these insights in modern physics and information theory, proposing specific mechanisms by which consciousness fields might interact with neural structures. The field approach also suggests that consciousness might not be limited to biological systems. If consciousness is a fundamental field, then appropriately organized artificial systems might also access or generate conscious experience. This has implications for artificial intelligence research and raises profound questions about the nature of machine consciousness. Experimental tests of field theories remain challenging, but researchers are beginning to develop protocols that might, in principle, detect field-like properties of consciousness. These experiments look for correlations between conscious states and field effects that appear to extend beyond the physical boundaries of the brain, using sensitive electromagnetic and gravitational detectors to search for possible signatures of consciousness fields. One of the most promising approaches to understanding consciousness has emerged from information theory and the study of complex systems. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes that consciousness corresponds to integrated information, the amount of information generated by a system that's more than the sum of its parts. This approach has the advantage of being mathematically precise and potentially measurable. Researchers can calculate the integrated information of different brain states and correlate these measurements with levels of consciousness. Early results show strong correlations between integrated information and conscious awareness, providing initial empirical support for information theoretic approaches to consciousness. Quantum versions of information integration theory suggest that consciousness might emerge from quantum information processing that creates integrated wholes from separate parts. Quantum entanglement provides a natural mechanism for this integration, allowing separate brain regions to share information in ways that classical physics cannot fully explain. In quantum information integration models, consciousness arises when quantum systems reach sufficient levels of integration and complexity. The subjective experience of awareness corresponds to the information processing patterns that these models propose may emerge from quantum entanglement and coherence across neural networks. This approach potentially bridges the gap between objective neural processes and subjective conscious experience. Instead of consciousness being something mysterious that emerges from unconscious matter, it becomes a hypothesized, measurable property of information integration in quantum systems. The hard problem of consciousness transforms into an engineering problem, understanding how biological systems might achieve the levels of quantum information integration necessary for awareness. Recent advances in quantum information theory have provided new tools for understanding these integration processes. Researchers can now calculate the quantum information capacity of biological systems and model how entanglement and coherence could contribute to information integration across neural networks. These theoretical developments are beginning to make contact with experimental neuroscience. Brain imaging studies have found that conscious states are characterized by specific patterns of information integration across neural networks, while unconscious states show reduced integration. If these integration patterns involve quantum processes, it would provide potential evidence for quantum theories of consciousness. As you reflect on these information integration approaches, consider how they might apply to your own conscious experience right now. The unified awareness you have of thoughts, sensations, and perceptions might reflect quantum information integration processes occurring across your neural networks, binding separate information processing events into the coherent stream of consciousness you're experiencing. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. The quantum consciousness debate has revitalized interest in Pansychism, the ancient philosophical idea that consciousness is a fundamental property of all matter. Modern panpsychist theories informed by quantum mechanics and information theory suggest that consciousness might be an intrinsic feature of quantum fields, rather than something that emerges only in complex biological systems. This approach potentially solves the hard problem of consciousness by eliminating the need to explain how subjective experience arises from objective processes. If consciousness is fundamental rather than emergent, then awareness doesn't need to be explained in terms of unconscious components. It's already present at the most basic levels of reality. Physicist and philosopher David Chalmers has argued that panpsychist interpretations of quantum mechanics might provide one of the more elegant solutions to both the measurement problem in physics and the hard problem of consciousness. If quantum events are associated with elementary forms of experience, then quantum measurement becomes a process of experiential selection rather than mysterious collapse. These quantum panpsychist theories face the combination problem. How do micro-experiences of individual particles combine to create the unified macro-experience of human consciousness? Quantum theories address this through entanglement and coherence, proposing that quantum correlations could, in theory, provide the binding mechanisms that create unified conscious experience from distributed micro-experiences. Recent work in quantum field theory has provided new mathematical frameworks for understanding how fundamental consciousness might organize itself into complex forms. These approaches draw on concepts from condensed matter physics and quantum many-body theory to model how elementary conscious processes might self-organize into the rich structures of human awareness. The panpsychist approach also has implications for artificial intelligence and machine consciousness. If consciousness is fundamental to matter and energy, then appropriately organized artificial systems might naturally develop conscious experience. This perspective suggests that machine consciousness might be easier to achieve than commonly assumed, requiring only the right kind of information integration rather than the replication of biological processes. Experimental tests of panpsychist theories remain challenging, but researchers are beginning to explore whether simple physical systems might exhibit very rudimentary forms of experience or awareness. These experiments look for signatures of information integration and quantum coherence in minimal systems, searching for the simplest possible forms of conscious experience. As quantum consciousness research advances, a profound picture is emerging of the relationship between mind and reality. Rather than consciousness being a passive observer of an independent physical world, awareness might be conceptualized as an active participant in the construction of reality itself. This participatory universe model suggests that consciousness and cosmos co-evolve together, with each shaping the other in an ongoing creative process. This perspective has roots in the participatory anthropic principle proposed by physicist John Wheeler, which suggests that the universe in some interpretations requires observers to bring it into existence. In Wheeler's participatory universe, observation isn't just about seeing, it's about participating in the ongoing creation of reality. This doesn't mean that individual human thoughts control the universe, but rather that consciousness and cosmos might be engaged in a much deeper dialogue than we've previously imagined. The universe, in this view, isn't a clockwork machine running independently of observers, but rather a creative process that unfolds through the interaction of matter, energy, information, and awareness. This participatory perspective finds support in quantum field theory, where the vacuum itself is alive with virtual particles and quantum fluctuations. If consciousness operates through quantum field processes, then awareness might be connected to the fundamental creative activity of the universe. Every moment of conscious experience might represent a localized flowering of the same creative processes that drive cosmic evolution. Recent research in quantum cosmology has suggested that the early universe might have undergone periods of quantum consciousness-like information processing during its formative stages. While this remains highly speculative, it raises the intriguing possibility that consciousness and cosmos have been co-evolving since the very beginning of time. Dr. Stuart Kauffman has proposed that consciousness might be related to what he calls the adjacent possible, the realm of potential that surrounds any given state of reality. In this view, conscious systems don't just respond to their environment but actively explore the space of possibilities, participating in the ongoing creativity that drives evolution and cosmic development. As you sit with these ideas, notice how they invite a different relationship with your own consciousness. Rather than being an isolated observer peering out at an alien universe, you might be a participating expression of cosmic creativity, intimately connected to the fundamental processes that shape reality itself. This perspective, while highly speculative and unproven, offers a profound sense of belonging and purpose in the cosmic story. The revolution in quantum biology has provided crucial support for quantum consciousness theories by demonstrating that biological systems routinely exploit quantum effects for essential life processes. What was once considered impossible, quantum coherence in warm biological environments, is now recognized as a plausible component of how life operates. Photosynthesis, the process that powers most life on Earth, achieves its remarkable efficiency through quantum coherence effects that allow energy to explore multiple pathways simultaneously before selecting the most efficient route. This quantum search algorithm, operating in the chloroplasts of every green plant, demonstrates that evolution has learned to harness quantum mechanics for information processing tasks. Bird navigation systems use quantum entanglement in cryptochrome proteins to sense magnetic fields with extraordinary precision. These biological quantum compass systems maintain entanglements at body temperature and in the presence of molecular noise that should destroy quantum effects according to classical calculations. Yet they function reliably enough to guide birds across thousands of miles of ocean. Our sense of smell might also depend on quantum tunneling effects that allow us to distinguish between molecules with identical shapes but different vibrational properties. This quantum nose theory remains controversial, but experimental evidence has been interpreted by some researchers as suggesting that olfaction involves quantum mechanical processes that classical biochemistry cannot explain. The discovery of quantum effects in photosynthesis, navigation, and possibly olfaction has forced scientists to reconsider their assumptions about the fragility of quantum coherence in biological systems. Rather than being destroyed by thermal noise and molecular chaos, quantum effects in biology appear to be surprisingly protected and even enhanced by the cellular environment. This quantum biology revolution has profound implications for consciousness research. If biological systems routinely use quantum effects for information processing, energy transfer, and sensing, then the brain, the most complex biological information processing system known, might also rely on quantum mechanisms for its most sophisticated functions. The transition from quantum biology to quantum consciousness isn't automatic, but it removes one of the strongest objections to quantum theories of mind. We now know that biological systems can maintain quantum coherence at body temperature, that evolution has discovered quantum solutions to information processing problems, and that quantum effects can be robust rather than fragile in living systems. Within this context of quantum biology, the Orch OR theory's focus on microtubules takes on new significance. Microtubules aren't just structural components of cells. They're sophisticated information processing systems that some researchers propose might function as biological quantum computers. Recent research has revealed that microtubules exhibit quantum properties that were previously thought impossible in biological systems. They display quantum vibrations at room temperature, maintain coherence across their length despite thermal noise, and even exhibit quantum superradiance effects when connected into larger networks. Dr. Anirban Bandyopadhyay's research group has demonstrated that microtubules can process information through quantum resonance effects, with different frequencies corresponding to different computational modes. These biological quantum computers might be capable of information processing tasks that are impossible for classical neural networks. The quantum computer model of microtubules suggests that each neuron might contain thousands of quantum processors working in parallel. Rather than consciousness emerging from the simple on-off firing of neurons, it might arise from hypothetical quantum computations occurring within the cellular infrastructure of the brain. This microtubule quantum computing hypothesis addresses several puzzles in neuroscience. It explains how the brain can perform computations that seem to require exponentially more processing power than classical neural networks can provide. It also suggests mechanisms for the rapid, parallel processing that characterizes conscious experience. If microtubules do function as quantum computers, then consciousness might involve quantum algorithms that explore vast spaces of possibility in parallel before collapsing into specific conscious experiences. This would make every moment of awareness a quantum computational event, processing information through superposition and entanglement in ways that classical computers cannot replicate. The quantum microtubule hypothesis also suggests that consciousness might be scalable in ways that classical theories cannot explain. By linking microtubules across neurons through quantum entanglement, the brain might create coherent, quantum computational networks that span large regions of neural tissue. The orchestrated aspect of Orch OR refers to the coordination of quantum processes across multiple microtubules and neurons. This orchestration might be guided by classical neural activity, but it would involve quantum computations that integrate information in ways impossible for classical systems. According to the theory, consciousness emerges when quantum superpositions in microtubular networks reach a critical threshold and undergo objective reduction. This reduction doesn't require external measurement or observation, but occurs spontaneously when the quantum system reaches sufficient complexity and integration. Each objective reduction event represents a moment of conscious experience, a quantum collapse that selects specific outcomes from the vast space of superposed possibilities. The sequence of these reduction events creates the stream of consciousness, with each moment building on previous reductions while exploring new possibilities. The orchestration process might involve feedback loops between classical neural activity and quantum computations. Neural firing patterns could influence the parameters of quantum computations, while quantum reduction events could influence neural activity patterns. This creates a dynamic system where classical and quantum processes co-evolve to generate conscious experience. Recent research has suggested that the orchestration might involve more than just microtubules within individual neurons. Quantum entanglement effects have been proposed as potentially coordinating microtubules across different neurons, creating brain-wide quantum computational networks that could underlie the unity and integration that characterizes conscious experience. This orchestrated quantum computation model suggests that consciousness isn't localized to any particular brain region, but may instead emerge from the coordinated quantum activity across multiple neural networks. This distributed quantum consciousness model aligns with neuroscientific evidence that conscious experience involves integrated activity across many brain areas. The study of anesthesia provides some of the most compelling theoretical evidence for quantum theories of consciousness. For over 150 years, doctors have been able to reversibly eliminate consciousness using various chemical agents. Yet the mechanism by which these diverse molecules erase awareness has remained largely mysterious. Classical neuroscience suggests that anesthetics work by disrupting neural communication, but this explanation faces several problems. Many anesthetic agents have very different chemical structures and target different neural systems, yet they all produce the same fundamental effect: the loss of consciousness. This suggests that they might be interfering with a common underlying mechanism. The quantum consciousness hypothesis proposes that anesthetics work by disrupting quantum processes in neural microtubules or other cellular structures. This would explain why chemically diverse anesthetics can produce similar effects on consciousness according to this model. They all interfere with the quantum processes that some researchers speculate may underlie awareness. Dr. Stuart Hameroff's research on anesthetic mechanisms has provided preliminary support for this quantum hypothesis. He's found that anesthetic potency correlates with the ability of anesthetic molecules to potentially disrupt quantum processes in microtubules. Agents that are more effective at disrupting microtubule quantum coherence tend to be more potent anesthetics. The xenon experiments we discussed earlier provide perhaps the strongest suggestive evidence for quantum effects in anesthesia. The fact that different isotopes of xenon, which differ only in their nuclear spin, produce different anesthetic effects suggests that consciousness might be sensitive to quantum properties of molecules. These isotope effects cannot be fully explained by classical neuroscience, which would predict that chemically identical molecules should produce identical biological effects. The quantum consciousness hypothesis, however, predicts exactly these kinds of isotope effects, since nuclear spin is a purely quantum property that could influence quantum processes in the brain. If confirmed by ongoing replication studies, these xenon isotope effects could provide important evidence that consciousness may depend on quantum processes. This would represent a paradigm shift in both neuroscience and our understanding of the nature of awareness itself. One of the deepest puzzles in consciousness research is the binding problem. How does the brain integrate separate sensory inputs, memories, and cognitive processes into the unified experience of consciousness? Classical neuroscience has struggled to explain how billions of separate neural events combine to create a single, coherent stream of awareness. Quantum theories of consciousness offer hypothetical solutions to the binding problem through entanglement and coherence effects. Quantum entanglement allows separate systems to become correlated in ways that transcend classical physics, creating genuine unity from apparent separation. If consciousness involves quantum entanglement between different brain regions, it could explain how separate neural processes bind together into unified experience. Rather than consciousness being constructed from separate pieces like a jigsaw puzzle, it might emerge as a coherent quantum state that's inherently unified. Dr. Henry Stapp has developed quantum models of consciousness that address the binding problem through what he calls quantum interactive dualism. In this model, conscious experience emerges from quantum entanglement between brain regions, while consciousness itself can influence brain activity through quantum measurement effects. This quantum approach to binding suggests that the unity of consciousness isn't something that needs to be constructed from separate parts, but rather is a fundamental property of quantum systems. The challenge isn't explaining how unity emerges from separation, but understanding how the inherent unity of quantum systems might manifest as conscious experience. Recent advances in quantum information theory have provided new mathematical tools for understanding these binding processes. Researchers can now calculate the entanglement entropy of different brain states and model how quantum correlations might contribute to the integration of neural information. These theoretical developments are beginning to make contact with experimental neuroscience. Brain imaging studies have found that conscious states are characterized by increased correlation between distant brain regions, while unconscious states show reduced long-range connectivity. If these correlations involve quantum entanglement, it would provide potential evidence for quantum binding in consciousness. The relationship between quantum mechanics and free will represents one of the most profound philosophical implications of quantum consciousness theories. If the brain operates as a quantum system, it might provide a mechanism for genuine choice and agency that doesn't violate physical laws. Classical deterministic physics seems to leave no room for genuine free will. If brain states are completely determined by prior physical states, according to classical laws, then our sense of making free choices might be an illusion. But quantum mechanics introduces genuine randomness and observer effects that might create space for authentic agency. Dr. Henry Stapp has proposed that quantum measurement processes in the brain provide a mechanism for conscious choice. In his model, the brain exists in quantum superposition until conscious observation selects specific outcomes. This selection process represents one possible interpretation of genuine choice that influences physical brain states while remaining consistent with quantum mechanics. This quantum free will hypothesis suggests that consciousness doesn't just observe brain activity, but may actively participate in determining brain states through quantum measurement effects. Rather than being passive observers of deterministic brain processes, we might be active participants in shaping our own neural activity. The quantum approach to free will faces several challenges. Critics argue that quantum randomness isn't the same as free choice, and that random events are no more freely chosen than deterministic ones. Defenders respond that quantum measurement involves more than mere randomness, but represents genuine selection from available possibilities. Recent research in quantum biology has shown that biological systems can influence quantum measurement outcomes through environmental effects and molecular organization. This suggests that evolved biological systems might be able to bias quantum processes in ways that transcend pure randomness, creating a form of theoretically possible quantum agency. The free will question remains unresolved, but quantum consciousness theories provide new frameworks for thinking about agency and choice, rather than being forced to choose between determinism and randomness. We might inhabit a quantum universe where genuine choice emerges from the interplay between consciousness and quantum possibility. The hard problem of consciousness, formulated by philosopher David Chalmers, asks why there is subjective experience at all. Even if we can explain all the cognitive functions of the brain, from memory to attention to decision-making, we still haven't explained why these processes are accompanied by inner experience. Why is there something it's like to be conscious? Classical neuroscience approaches the hard problem by trying to identify neural correlates of consciousness, brain states that correspond to conscious experiences. But finding correlations doesn't explain why those neural states should be associated with subjective experience rather than occurring in the dark without any inner phenomenology. Quantum consciousness theories approach the hard problem differently. Rather than trying to explain how subjective experience emerges from objective neural processes, they suggest that experience might be fundamental to the quantum processes that underlie neural activity. In this view, consciousness doesn't emerge from unconscious matter, but represents an intrinsic aspect of quantum information processing. If quantum events are associated with elementary forms of experience, then the hard problem dissolves. We don't need to explain how consciousness arises from unconscious components, because consciousness is already present at the quantum level. The challenge becomes understanding how elementary conscious events combine and organize into the rich experience of human awareness. This quantum panpsychist approach draws on mathematical frameworks from quantum field theory and information theory to model how elementary conscious processes might self-organize into complex forms of awareness. These models suggest that consciousness might be scalable in ways that classical theories cannot explain. Recent work in integrated information theory has provided mathematical tools for quantifying consciousness in quantum systems. If consciousness corresponds to integrated information, then quantum entanglement and coherence provide natural mechanisms for creating the information integration that underlies conscious experience. The quantum approach to the hard problem remains highly speculative, but it offers a fundamentally different perspective on the nature of consciousness and its relationship to physical processes. Rather than consciousness being an emergent property that needs to be explained, it becomes a fundamental aspect of reality that helps explain other phenomena. If consciousness is indeed a fundamental feature of quantum processes, the implications extend far beyond neuroscience into cosmology and our understanding of the universe itself. Some researchers have proposed that consciousness might be connected to the fundamental creative processes that drive cosmic evolution. The anthropic principle in cosmology notes that the universe appears to be fine-tuned for the existence of conscious observers. The fundamental constants of physics, from the strength of gravity to the charge of the electron, seem precisely calibrated to allow for the formation of stars, planets, and ultimately life and consciousness. Wheeler's participatory anthropic principle goes further, suggesting that consciousness might play an active role in determining the properties of the universe. In this view, the universe doesn't just happen to be suitable for consciousness. It's shaped by the requirement that conscious observers must eventually emerge. If consciousness operates through quantum processes, then the participatory universe model gains a specific physical mechanism. Conscious observation might not just reveal pre-existing reality, but participate in its ongoing construction through quantum measurement effects that operate across all scales of space and time. This cosmic consciousness hypothesis remains highly speculative and faces numerous scientific and philosophical challenges, but it represents a profound shift from viewing consciousness as an accidental byproduct of cosmic evolution to seeing it as a fundamental participant in the creative processes that shape reality itself. Recent research in quantum cosmology has suggested that the early universe might have undergone periods of quantum information processing that resemble consciousness-like activity. While this doesn't prove that the universe is conscious, it suggests that information, processing, and consciousness-like phenomena might be more fundamental to cosmic evolution than previously thought. The practical implications of quantum consciousness research are beginning to emerge in cutting-edge technology development. If consciousness does involve quantum processes, then the interface between human minds and quantum computers might lead to hybrid systems with unprecedented capabilities. Google's quantum consciousness experiments represent the first steps toward brain-quantum computer interfaces that could revolutionize both computing and our understanding of consciousness. These systems might eventually allow direct neural control of quantum computers or enhancement of human cognitive abilities through quantum processing. The development of quantum-enhanced neural interfaces raises profound questions about the nature of human consciousness and identity. If our minds can directly interface with quantum computers, where does human consciousness end and artificial quantum processing begin? These questions will become increasingly important as the technology develops. Brain-computer interfaces are already beginning to restore function to people with paralysis and other neurological conditions. If consciousness involves quantum processes, then quantum-enhanced neural interfaces might provide even more sophisticated restoration of function or enhancement of cognitive abilities. The possibility of quantum consciousness also has implications for artificial intelligence research. If consciousness requires quantum processing, then truly conscious artificial intelligence might require quantum computers rather than classical digital systems. This could explain why current AI systems, despite their impressive capabilities, lack the subjective experience that characterizes human consciousness. Conversely, if quantum computers can support consciousness-like phenomena, then we might be approaching the development of genuinely conscious artificial systems. This would raise profound ethical questions about the rights and status of artificial conscious beings. Understanding the quantum basis of consciousness might also lead to new therapeutic approaches for disorders of consciousness and mental health. If consciousness depends on quantum coherence in neural microtubules, then treatments that enhance or restore quantum coherence might help with conditions like depression, schizophrenia, or disorders of consciousness. Some researchers have proposed that meditation and other contemplative practices might work by enhancing quantum coherence in the brain. While this remains speculative, studies of meditation have shown that contemplative practices can produce measurable changes in brain activity and structure that some theorists interpret as potentially reflecting altered quantum processing. Dr. Eben Alexander, a neurosurgeon who experienced a profound near-death experience during a coma, has proposed that consciousness might not be entirely produced by the brain, but accessed through quantum processes. While his interpretations remain controversial, his case has sparked scientific interest in the relationship between brain injury, quantum processes, and consciousness. The development of quantum-based therapies for consciousness disorders remains in its infancy, but the theoretical foundations are beginning to emerge. If consciousness does involve quantum processes, then understanding and manipulating these processes might provide new approaches to treating the most challenging disorders of mind and awareness. Anesthesiology might also benefit from quantum consciousness research. Understanding the quantum mechanisms of anesthetic action could lead to more precise and safer anesthetic agents, reduced side effects, and better control over the depth and duration of unconsciousness. Perhaps the most profound implications of quantum consciousness research are philosophical. If consciousness is indeed fundamental to quantum mechanics, it challenges the materialist worldview that has dominated science for centuries. Rather than consciousness being an emergent property of complex matter, matter and consciousness might be co-fundamental aspects of reality. This shift toward a consciousness-inclusive physics doesn't necessarily embrace supernatural or mystical interpretations, but it does suggest that consciousness deserves a place in our fundamental theories of reality. This could lead to a new scientific worldview that integrates subjective experience with objective physical processes. The integration of consciousness into physics also has implications for our understanding of personal identity and the nature of the self. If consciousness operates through quantum processes that extend beyond individual brains, then the boundaries of the self might be more fluid than commonly assumed. Some interpretations of quantum consciousness suggest that individual minds might be localized expressions of a more fundamental consciousness field. This field theory of consciousness has parallels with various mystical and philosophical traditions, but it attempts to ground these insights in mathematical physics and experimental science. The philosophical implications extend to questions of meaning and purpose in the universe. If consciousness plays a fundamental role in quantum mechanics and cosmic evolution, then the universe might be interpreted as inherently meaningful rather than accidentally so. This doesn't prove the existence of cosmic purpose, but it suggests that consciousness and meaning could be more fundamental than materialist science has typically assumed. Take a moment here to reflect on these philosophical implications. If consciousness is indeed quantum mechanical, then your awareness right now might be participating in the same fundamental processes that operate throughout the universe. The thoughts you're thinking, the experiences you're having, might be expressions of quantum creativity that some theories propose may connect you to the deepest levels of reality. The future of quantum consciousness research lies in increasingly sophisticated experiments that can directly test the predictions of quantum theories of mind. These experiments will require advances in both neuroscience technology and quantum measurement techniques. One promising direction involves using quantum sensors to detect possible quantum effects in living brain tissue. These sensors, based on quantum systems like nitrogen vacancy centers in diamond, can detect magnetic fields and other quantum signatures with unprecedented sensitivity. If consciousness involves quantum processes, these sensors might be able to detect them directly. Another experimental approach involves studying the quantum properties of isolated neural microtubules and other cellular structures. Researchers are developing techniques to maintain biological quantum coherence in controlled laboratory conditions, allowing detailed study of potential quantum processes in biological systems. Brain imaging technology is also advancing to the point where it might be able to detect indirect quantum-related signatures of consciousness. New techniques that combine multiple imaging modalities might reveal patterns of brain activity that reflect quantum rather than classical information processing. The development of more sophisticated quantum computers will also provide new tools for testing quantum consciousness theories. These systems might be able to simulate the quantum processes hypothesized to occur in the brain, allowing researchers to test whether such processes could indeed support consciousness. Perhaps most importantly, the experimental study of quantum consciousness will require interdisciplinary collaboration between physicists, neuroscientists, computer scientists, and philosophers. The questions involved are too complex for any single discipline to address alone. One of the biggest challenges facing quantum consciousness research is the replication of experimental results. Many of the key experiments in the field have been difficult to reproduce consistently, leading to skepticism about their validity. These xenon isotope experiments that show different anesthetic effects for different nuclear spins are being replicated in laboratories around the world. If these results are confirmed, they could provide significant evidence for quantum effects in consciousness. If they fail to replicate, it would be a substantial challenge for quantum consciousness theories. The double-slit consciousness experiments, where human attention appears to influence quantum interference patterns, have also shown mixed replication results. Some laboratories report positive effects, while others find no significant influence of consciousness on quantum systems. The challenge of replication in quantum consciousness research reflects the subtle nature of the effects being studied. If consciousness does influence quantum systems, the effects might be small, context-dependent, and easily disrupted by uncontrolled variables. This doesn't necessarily invalidate quantum consciousness theories, but it highlights the need for more sophisticated experimental protocols and better understanding of the conditions under which any possible effects might be detectable. The replication crisis in quantum consciousness research also reflects broader challenges in studying consciousness scientifically. Consciousness is inherently subjective and difficult to measure objectively, making it challenging to design experiments that can definitively test theories about its nature. The scientific response to quantum consciousness theories has been mixed, with many researchers remaining skeptical of claims that consciousness involves quantum processes. This skepticism is based on several legitimate concerns about the theoretical foundations and experimental evidence for quantum consciousness. One major concern is the decoherence problem we discussed earlier. Critics argue that quantum effects in the warm, noisy environment of the brain would be destroyed too quickly to influence neural processing or consciousness. While quantum biology has shown that some biological systems can maintain quantum coherence, skeptics argue that the brain's complexity makes it unlikely to support the coherent quantum processes required by consciousness theories. Another concern involves the lack of clear predictions from quantum consciousness theories. Critics argue that these theories are often vague about exactly what quantum processes are supposed to occur and how they would influence consciousness. Without specific testable predictions, it's difficult to evaluate the theories scientifically. The experimental evidence for quantum consciousness also faces criticism. Many of the key experiments have small effect sizes, limited replication, and alternative explanations that don't require quantum effects. Critics argue that extraordinary claims require extraordinary evidence, and that quantum consciousness theories haven't yet met this standard. Some skeptics also worry that quantum consciousness theories are being used to support unscientific or pseudoscientific beliefs about the power of consciousness to influence reality. While legitimate scientific theories should be evaluated on their own merits, the association with fringe ideas has made some researchers hesitant to engage with quantum consciousness research. Despite these criticisms, the field continues to advance through better experimental designs, more sophisticated theoretical models, and increasing dialogue between proponents and skeptics. This scientific discourse is essential for determining whether quantum consciousness theories will ultimately be supported or refuted by evidence. As quantum consciousness research matures, a more nuanced picture is emerging that integrates quantum and classical approaches to understanding awareness. Rather than consciousness being purely quantum or purely classical, it might involve complex interactions between quantum and classical processes at multiple scales. This integrative approach suggests that consciousness might emerge from the dynamic interplay between quantum coherence and classical decoherence, with both processes contributing essential features to conscious experience. Quantum processes might provide the unity and integration that characterizes consciousness, while classical processes might provide the stability and specificity that allows consciousness to interact with the environment. Recent theoretical work has developed models of consciousness that incorporate both quantum and classical elements in sophisticated ways. These hybrid models attempt to capture the advantages of quantum information processing while addressing the challenges of maintaining quantum coherence in biological systems. The integrative approach also recognizes that different aspects of consciousness might involve different physical processes. Attention, memory, perception, and self-awareness might each depend on different combinations of quantum and classical mechanisms operating at different scales in the brain. This pluralistic view of consciousness aligns with the complexity of conscious experience itself. Rather than seeking a single explanation for all aspects of consciousness, researchers are beginning to develop multiple complementary theories that address different features of awareness. The integration of quantum and classical approaches also has practical implications for consciousness research. It suggests that understanding consciousness will require tools and concepts from multiple scientific disciplines, from quantum physics to neuroscience to computer science. Looking ahead, quantum consciousness research is likely to become increasingly sophisticated and empirically grounded. Advances in quantum technology, brain imaging, and theoretical modeling will provide new tools for testing quantum theories of mind. The development of quantum sensors and quantum computers will enable more precise measurements of potential quantum effects in biological systems. These tools might finally provide definitive evidence for or against quantum processes in consciousness. Brain imaging technology will also continue to advance, potentially reaching the point where it can detect subtle, quantum-related signatures of consciousness directly. New imaging techniques that combine multiple modalities might reveal patterns of brain activity that reveal patterns that transcend classical neural networks entirely. We might soon witness the first suggestive observations of quantum coherence in conscious neural processes, bridging the gap between theoretical speculation and empirical reality. The field is also likely to become more interdisciplinary, with researchers from physics, neuroscience, computer science, and philosophy working together to address questions that no single discipline can answer alone. This collaboration might lead to entirely new conceptual frameworks that transcend traditional boundaries between mind and matter. Educational institutions are beginning to develop programs that train researchers in both quantum physics and consciousness studies, creating a new generation of scientists equipped to tackle these interdisciplinary challenges. This educational evolution suggests that quantum consciousness research will become increasingly mainstream over the coming decades. As we approach the final chapters of our exploration tonight, consider how the very act of measuring consciousness might be transformed by quantum technologies. Traditional neuroscience relies on indirect measurements of brain activity, observing the shadows of consciousness rather than consciousness itself. But quantum measurement techniques might provide new ways to explore the quantum processes that some theorists propose may underlie awareness. Quantum sensors based on nitrogen vacancy centers in diamond can detect magnetic fields with sensitivity approaching the fundamental quantum limits. These sensors, smaller than viruses yet more sensitive than room-sized instruments, might soon be deployed within living neural tissue to detect possible quantum signatures of consciousness directly. Imagine microscopic quantum sensors distributed throughout the brain, each one capable of detecting individual quantum events in real time. Such a system might reveal patterns of quantum activity that correlate with specific conscious experiences, providing highly experimental and exploratory insights into quantum consciousness processes. These measurement technologies raise profound questions about the relationship between observation and consciousness. If consciousness involves quantum processes, then quantum measurements of consciousness might involve consciousness observing itself at the quantum level. This creates a recursive loop that challenges traditional distinctions between observer and observed. Dr. Lucienne Hardy at the Perimeter Institute has proposed experiments that could test whether consciousness can influence its own quantum measurement. These experiments would involve conscious observers attempting to influence quantum measurements of their own brain activity, creating a direct test of hypothetical consciousness-matter interaction. The results of such experiments could reshape our understanding of the relationship between mind and measurement in quantum mechanics. If consciousness can influence quantum measurements of itself, it would suggest that the observer effect in quantum mechanics might be more intricately connected to observation than traditionally assumed. Recent advances in quantum information theory have revealed that information itself has geometric properties existing in abstract mathematical spaces with their own intrinsic structure. If consciousness involves quantum information processing, then awareness might conceptually inhabit these information geometries. These information spaces have curvature, topology, and other geometric properties that could correspond to different aspects of conscious experience. The subjective sense of moving through thoughts and memories might reflect genuine motion through information space, with conscious experience tracing paths through landscapes of possibility. Dr. Chris Fields, working at the intersection of physics and cognitive science, has proposed that consciousness might be understood as navigation through quantum information space. In this model, each moment of awareness corresponds to a specific location in information geometry, with the flow of consciousness representing movement through these abstract mathematical landscapes. This geometric approach to consciousness provides new tools for understanding how subjective experience relates to objective neural processes. Rather than consciousness being something that emerges from brain activity, it might be something that brain activity interacts with or maps onto, with neural networks serving as biological guidance systems for exploring information space. The geometric perspective also suggests that consciousness might have topological properties, features that remain invariant under continuous deformation. This could explain why consciousness maintains its essential character, despite constant changes in neural activity and environmental conditions. As you reflect on these geometric metaphors for consciousness, notice how they invite you to think spatially about your own awareness, the thoughts you're having right now. The shift from one idea to another might represent genuine movement through dimensions of experience that exist as real mathematical structures in information space according to this theoretical framework. One of the deepest mysteries in consciousness research involves emergence, the process by which complex systems develop properties that their individual components don't possess. Classical emergence, like the wetness of water emerging from dry molecules, seems insufficient to explain the qualitative leap from unconscious neural activity to conscious experience. Quantum emergence operates according to different principles, where wholes can be genuinely greater than the sum of their parts in ways that classical physics cannot explain. Quantum entanglement creates correlations between particles that cannot be reduced to the properties of individual particles, generating genuinely novel phenomena that transcend classical emergence. If consciousness involves quantum emergence, then awareness might represent a qualitatively new level of reality that arises from but cannot be reduced to neural activity. This quantum emergence could explain how subjective experience can be real and causally effective while remaining irreducible to objective physical processes. Dr. Stuart Kauffman has proposed that consciousness might be an example of what he calls ontological emergence, where new levels of reality actually come into existence rather than simply appearing to emerge from below. In this view, quantum consciousness would be genuinely creative, bringing new aspects of reality into being through the process of awareness itself. This creative emergence perspective suggests that consciousness doesn't just observe reality, but participates in its ongoing construction. Each moment of awareness might represent a small act of cosmic creativity, contributing to the unfolding story of the universe through quantum processes that transcend classical determinism. The emergence paradox also touches on questions of causation and free will. If consciousness emerges from quantum processes in ways that transcend classical emergence, it might possess genuine causal powers that allow it to influence the physical processes from which it arises. This would provide a mechanism for top-down causation that doesn't violate physical laws. Recent research has revealed that consciousness might involve coherence networks that extend across both space and time in ways that classical neuroscience cannot explain. These networks might use quantum entanglement to create correlations between brain regions separated by distances that classical signals cannot bridge in the time available. Dr. Enzo Tagliazucchi's research group has discovered that conscious brain states exhibit long-range correlations that appear to exceed classical limits on information transfer. These correlations suggest that consciousness might involve non-classical or possibly quantum-related processes that create genuine unity across spatially separated neural networks. The temporal aspects of these coherence networks are equally mysterious. Consciousness seems to bind events occurring at different times into unified experiences, creating the sense of temporal flow and narrative continuity that characterizes awareness. Quantum theories suggest that this temporal binding might involve quantum correlations that transcend classical limitations on temporal correlation. If consciousness involves quantum coherence networks, then the boundaries of individual minds might be more fluid than commonly assumed. Quantum entanglement effects might create correlations between different brains under certain conditions, potentially explaining phenomena like empathy, emotional contagion, and the social aspects of consciousness from a speculative standpoint. These coherence networks might also extend beyond individual lifetimes, connecting consciousness across generations through quantum information storage in biological systems. While highly speculative, this possibility suggests that consciousness might have transgenerational aspects that transcend individual brain function. The study of coherence networks in consciousness is still in its infancy, but it represents one of the most promising directions for understanding how quantum effects might scale up to create the large-scale unity that characterizes conscious experience. The observer effect in quantum mechanics takes on new meaning when applied to consciousness research. If consciousness involves quantum processes, then studying consciousness scientifically creates a situation where quantum systems are observing themselves, potentially altering their own behavior through the act of observation. This recursive self-observation might explain some of the challenges in consciousness research, where the act of studying consciousness seems to change its nature. Traditional scientific methods assume a clear separation between observer and observed, but consciousness research might require new methodologies that account for the participatory nature of conscious observation. Dr. Amit Goswami has proposed that consciousness research represents a new kind of science, where the observer is included as an essential part of the experimental system. This participatory science would recognize that consciousness cannot be studied purely objectively because consciousness is always involved in the act of observation itself. The self-referential nature of consciousness research also has implications for artificial intelligence and machine consciousness. If consciousness involves deeply complex or potentially quantum-related processes, then creating conscious machines might require systems capable of advanced, possibly self-referential monitoring and self-modification. These recursive aspects of consciousness research challenge traditional notions of scientific objectivity while opening up new possibilities for understanding awareness. Rather than being a limitation, the participatory nature of consciousness research might be essential for understanding how consciousness may operate according to certain theoretical interpretations of the quantum realm. If consciousness does involve quantum processes, the implications for healing and therapy could be profound. Understanding the potential quantum basis of awareness might lead to entirely new approaches to mental health that work directly with the hypothesized quantum foundations of consciousness. Some researchers have proposed that meditation and other contemplative practices might work by enhancing quantum coherence in neural systems. While this remains speculative, studies of meditation have shown effects on brain activity that some interpret as possibly consistent with altered information processing, though no scientific consensus exists on this interpretation. Dr. Deepak Chopra, working with quantum physicists, has explored connections between consciousness, quantum mechanics, and healing, though these ideas remain controversial, exploratory, and not established within mainstream science. The challenge lies in distinguishing legitimate scientific hypotheses from speculative claims about consciousness and healing. Anesthesiology might also be transformed by quantum consciousness research. If anesthetics work by disrupting underlying quantum-related processes in the brain, understanding these mechanisms could lead to more precise and safer anesthetic agents with fewer side effects and better control over consciousness states. The development of quantum-based therapies for consciousness disorders remains highly speculative, but the theoretical foundations are beginning to emerge. If consciousness does involve quantum processes, then learning to influence these processes therapeutically might provide new approaches to treating depression, anxiety, and other disorders of awareness. As our exploration draws toward its close, we encounter perhaps the most profound implication of quantum consciousness research: the possibility that individual awareness is connected to the fundamental creative processes of the universe itself. This connection, if it exists, would not be mystical or supernatural, but would operate through the same quantum processes that govern the behavior of particles and fields throughout the cosmos. The quantum vacuum, that seemingly empty space between particles, seethes with virtual particle creation and annihilation events. If consciousness involves quantum field processes, then awareness might be connected to this fundamental activity of the universe, participating in the ongoing creativity that manifests as physical reality. This cosmic perspective on consciousness doesn't diminish the importance of individual awareness, but places it in a larger context of universal creativity and information processing. Every moment of consciousness might represent a localized flowering of the same creative intelligence that drives cosmic evolution and the emergence of complexity throughout the universe. Dr. Stuart Hameroff has speculated that consciousness might be connected to the fundamental information processing that occurs in the quantum vacuum, though this remains an unproven hypothesis without scientific consensus. If true, it would suggest that consciousness is not an accidental byproduct of cosmic evolution, but possibly an intrinsic feature of how the universe processes information and generates novelty. These cosmic connections remain speculative, but they invite us to consider consciousness not as an isolated phenomenon confined to individual brains, but as an expression of universal principles that operate across all scales of reality. This perspective, while not proven by current science, offers a profound sense of connection and meaning that transcends individual existence. In the quantum realm, reality seems to operate more like a democracy than a dictatorship. No single particle or process determines outcomes. Instead, quantum systems explore multiple possibilities simultaneously before settling into specific states through collective processes that remain mysterious. If consciousness operates according to this theoretical quantum democratic principle, then awareness might emerge from the collective behaviour of countless potentially quantum-related processes, rather than being controlled by any single neural mechanism. This quantum democracy model suggests that consciousness is distributed and participatory rather than centralised and hierarchical. The implications of quantum democracy for understanding free will and agency are profound. Rather than choices being made by a central executive self, decisions might emerge from quantum democratic processes that explore multiple possibilities before settling on specific outcomes. This would make free will a metaphorical or theoretical collective quantum phenomenon rather than an individual classical one. Dr. Freeman Dyson, the legendary physicist, once speculated that mind in nature might be universal, operating through quantum processes at all scales from particles to galaxies. While highly speculative, this quantum panpsychist view suggests that consciousness might be a fundamental feature of how the universe processes information and makes choices. The democratic nature of quantum processes also suggests that consciousness might be more egalitarian than hierarchical, with different aspects of awareness having equal voice in the collective processes that generate conscious experience. This interpretive quantum democracy might explain why consciousness often feels like a conversation between different aspects of the self, rather than a monolithic unity. The revolution in quantum information theory has revealed that information might be more fundamental than matter or energy, with physical reality emerging from underlying information processing rather than the other way around. If consciousness represents the universe's most sophisticated information processing system, then awareness might play a central role in the construction of reality itself. This information theoretic view of consciousness suggests that the hard problem of consciousness, explaining how subjective experience arises from objective processes, might be based on incorrect assumptions. Perhaps consciousness doesn't emerge from unconscious matter, but represents an intrinsic feature of how information organizes itself into coherent patterns. Quantum information processing operates according to principles that transcend classical computation, using superposition and entanglement to explore vast spaces of possibility in parallel. If consciousness involves quantum information processing, then awareness might have computational capabilities that exceed anything achievable through classical neural networks. The quantum information approach also suggests that consciousness might be scalable in ways that classical theories cannot explain. By linking quantum information processing systems through entanglement, consciousness might extend across multiple brains, or even interface with artificial quantum systems to create hybrid forms of awareness. These information theoretic perspectives on consciousness remain speculative, but they're grounded in solid mathematics and experimental physics. The tools of quantum information theory are providing new languages for describing consciousness that bridge the gap between subjective experience and objective physical processes. At the heart of quantum mechanics lies the measurement problem, the mystery of how quantum possibilities become classical realities. Some interpretations suggest that consciousness plays a special role in this process, not just observing quantum systems, but participating in their transition from potential to actual. If consciousness does participate in quantum measurement, then the act of awareness might be fundamentally creative, helping to determine which possibilities become real rather than simply observing pre-existing realities. This would make consciousness an active participant in the ongoing construction of the universe, rather than a passive observer. The measurement problem takes on new dimensions when applied to consciousness itself. If consciousness involves quantum processes, then studying consciousness scientifically creates situations where quantum systems are measuring themselves, potentially altering their own behaviour through the act of self-observation. Dr. Henry Stapp has developed quantum mechanical models of consciousness that address these measurement mysteries by proposing that conscious observation represents a fundamental type of quantum measurement that bridges the gap between potential and actual. While controversial, these models provide specific mechanisms for understanding how consciousness might influence physical reality through quantum processes. The measurement mysteries of quantum consciousness research challenge traditional scientific methodologies while opening up new possibilities for understanding the relationship between mind and reality. They suggest that consciousness research might require participatory approaches that recognize the active role of awareness in shaping what we study. Quantum entanglement creates connections between particles that transcend classical limitations of space and time, suggesting that reality might be more interconnected than our everyday experience suggests. If consciousness involves non-classical or quantum-related forms of entanglement, then individual minds might be connected in ways that classical neuroscience cannot explain. These entanglement connections might operate below the threshold of ordinary awareness, creating subtle influences between minds that appear as intuition, empathy, or emotional contagion. While highly speculative, this possibility suggests that consciousness might have non-local aspects that extend beyond individual brains. The social dimensions of consciousness, from shared emotions to collective decision-making, might involve quantum entanglement effects that create genuine connections between minds. These connections would not violate individual autonomy, but might provide mechanisms for the social aspects of consciousness that seem to transcend classical neural communication. Recent research in quantum biology has shown that entanglement effects can persist in biological systems under conditions that were previously thought impossible. If similar entanglement effects operate in neural systems, they might provide the basis for theoretical, non-local aspects of consciousness. The study of entanglement in consciousness remains at the frontiers of both theoretical and experimental research, but it represents one of the most intriguing possibilities for understanding how awareness might transcend the boundaries of individual brains. Imagine consciousness as a vast symphony where billions of quantum processes play together in harmonious coherence, creating the melody of awareness through their coordinated activity. This musical metaphor captures something essential about how quantum coherence might generate the unified experience of consciousness from countless separate processes. So here we are, having travelled together through the strange and beautiful landscape where consciousness meets quantum mechanics. We've explored underground laboratories carved from solid rock, witnessed experiments with xenon gases that respond to quantum spin, and contemplated theories that suggest awareness itself might be woven into the fundamental fabric of reality. What emerges from this journey isn't a simple answer to whether consciousness is a particle, but rather a deeper appreciation for the mystery of awareness itself. The evidence continues to accumulate, from quantum effects in microtubules to the discovery of superradiance in biological systems. Yet the questions grow richer rather than simpler. Perhaps that's exactly as it should be. Perhaps consciousness, like quantum mechanics itself, isn't meant to fit neatly into our everyday categories of understanding. Whether consciousness turns out to involve quantum processes or operates through mechanisms we haven't yet imagined Tonight's exploration reminds us that awareness is far stranger and more wonderful than we typically assume. Every moment of your consciousness, every thought that flows through your mind, participates in processes that connect you to the deepest mysteries of existence. That possibility alone is enough to transform how we think about ourselves and our place in the universe. The conversation between physics and consciousness is just beginning, and the implications stretch far beyond academic debates into questions about healing, technology, and what it means to be human in a quantum universe. As we continue to probe these mysteries with ever more sophisticated tools and theories, we're not just studying consciousness, we're participating in its ongoing evolution. Until next time, rest well in the knowledge that your awareness, however it operates, represents something truly extraordinary in the cosmic story. If you'd like to explore how the mathematical foundations of quantum mechanics might themselves be more than mere calculation, join me for Quantum Consciousness Explained. Does the wave function actually exist? Sleep gently and dream of possibilities.